Good morning, everyone. So indeed, this is the first part of a McMule double bill. I will start and tell you a little bit about the framework, how we do QED calculations. And you'll see it's actually different than all other calculations, or there are quite some differences to the calculations, the other calculations I've presented here. And I've tried to point out what these differences are and why we do things the way we do them. In the second part, Yannick will present a collection of results. So you see, this is not just empty talk, but in fact, it has been applied and results are available. So McMule stands for Monte Carlo for muons and other leptons. It's really calculations for point-like particles. So that's why we call it leptons. And this thing has already originated at PSI. So and for PSI physicists, muons, that they have a special place in our heart, and that's why we sort of, I mean, it has started with muon decay, and that's why this is sort of reflected in the name. It's available on GitLab, and it will be, whenever there is a new process, it will be updated, and you can download it from there. And you see, it's quite a list of people connected to this. That doesn't mean that all these people work full-time 100% on this, but there is still about 12 people or so that have sort of contributed in some way, shape, or form to this. So it is fixed order QED calculation, as I said, for scattering and decay processes. Some of them are NNLO, but in this talk, I'll focus on NNLO. Okay. We're also toying with 1N more, but this is for the future. Okay, but it is sort of emerging. And then you see that there's at the moment no, well, I should say, no dirty two-photon exchange. Okay, it's just that the point-like two-photon exchange is included, but nothing that has to sort of resembles of hadronic stuff. Okay, and we have no parton shower yet, and I have on purpose used the LHC terminology of parton showers. You would call this exponentiation or structure function approach or fragmentation function approach, but I use the QCD and LHC language, and that has much to do with the last line, which is in some sense the most important line of the talk. And I'll come back to that in a second. So what it is, it's a fully differential Monte Carlo integrator. So you can make whatever cuts you want. You can decide how you treat the additional photons, the radiative photons that are emitted, how you treat them, whatever you want, as long as it's infrared safe. You can put these cuts in, and the code will give you a distribution. It will not give you events at this moment in time. I understand that. I understood it before. I understand it much better now that events are important for you and you would like to have events. At the moment, the mule is a bit too stubborn for this, but who knows, with a few carrots, maybe at some point it will do that. Okay, so that's it's in the back of our heads. And when I say NNLO, then I really mean NNLO, okay, really. And I say here, we make no approximation at all. And if you pay attention, you'll find out this is a bit of a lie. At some point, in fact, we do make an approximation. I'll point this out where it is, okay. And now this is the last line. This is the most important line of the whole talk. So, right, so I'm standing here and say we can do things that so far nobody else could do in QED. And why is this? This is not because we're more clever than the others. It's because we are better thieves. Really, it's as simple as that. So we steal or we use results that have been developed in the connection of QCD calculations at the LHC, or is it electroweak calculations, whatever, from the energy frontier. And that is maybe something we should, as a community, realize here. This community for LHC physics is much, much larger than ours. So we have literally hundreds of theorists working for tens of years, each and every one. And they do calculations that are really quite similar to ours. And not all of these guys are complete fools, okay? So why don't we just use these results? And that's what we do, okay? And sometimes I was sitting here and listening to talks, and someone said, oh, now we have to do this, and this is very difficult. And I wanted to shout, no, it's not. It's not. if you want to cut a tree and you use a pocket knife, this is very difficult. But then for heaven's sake, use a chainsaw, right? In particular, if the chainsaw is lying there in front of you and it's free of charge. Okay, maybe you want to spend half an hour to learn how to use the chainsaw, otherwise you might hurt yourself, but invest this time and use the chainsaw, okay? Then it's not difficult to cut a tree. That's the most important statement. So I mentioned this QCD and LHC stuff and then connect to the QED and at low energies. So what is the same, what is different? So QCD obviously is non-abelian. QED is abelian. That means QED is in that sense simpler. It is a bit simpler for calculating the matrix elements because the algebra is a bit simpler, but actually the difference is not so large. So if you want the most complicated loop integral that you have to do in QCD is the same as in QED. The algebra is a bit simpler, but if you do the algebra by hand, then you get anyway what you deserve, right? We do it by computer, and whether my expression is that or that, what do I care, right? I don't care so much. That's a small difference. Where there is a really, really big difference is in the infrared structure. That is so infinitely much easier in QED. So this is when QCD people get jealous, okay? So it's this combining of real and virtual corrections that, and that is my point one. So you have 3 points. The first point is how I will explain to you how we exploit, how we take QCD calculation and exploit this simple structure infrared singularities in QED and can make further progress. The second difference is that in QCD or LHC calculation, typically the fermions are massless. Well, the top quark, of course not, but all the others are treated as massless. Whereas we really want to keep the fermion masses. Our fermions are always massive, they're never massless. And that is very bad for loop calculations because this is an additional scale. And those of you who have done loop integrals know every scale is you get punished a lot. So that makes it much more difficult. So that's point two I will address. This is where our calculations are more difficult than the QCD calculations. And the third point is related to how exclusive we are with respect to collinear radiation. So we want to be exclusive, right? We have an electron, and whether or not it emits a collinear photon makes a difference. And we see a difference in the experiment. In QCD, they do jets. All this collinear radiation, it just goes into a jet. So it doesn't matter whether it emits or not. It's inclusive with respect to collinear emission. And for initial state, it's inclusive because it's put into the pattern distribution functions. But we don't. And if you have this collinear radiation, we have this seen several times, we get this logarithm, m squared over q squared. M squared is the fermion mass. Q squared is any large scale of the process. I will call this capital L throughout, that we have seen this before. I mean, you have used the same notation for this awful logarithm. And so that makes it harder. And in particular, if this m is small compared to q, it makes it much harder for numerical reasons. So we do a calculation, we have these large contributions in there, and sort of we have to make the numerics such that we get those plus the other terms as well. And that's my third point. I will discuss how we deal with this. And again, apart from this roughly speaking, apart from these three differences, we just steal master integrals, how we the reduction, integration by parts, the computation, that is how all these automated tool studies, we just use them. Effective field theory methods have been developed, we just use them and apply them. We use dimensional regularization for infrared singularities, no photon mass. Why? For a photon, it's perfectly fine to introduce a mass, but for a gluon, you don't want to introduce a gluon mass, really. And so the calculations in QCD are always done with massless gluons. We want to steal, so our photon is massless. Okay? We use dimensional regularization. We use the subtraction method, not the slicing method. I'll tell you what this is. And then the last point, as I said, at some point, whenever we get to do that, it is this matching to the fixed order result of parton showers, we will steal again, because this is something, again, that has been done at the LHC. Just a remark for the chair. If you look at the time and how I progress with the slides, and you start to get nervous because you think I'm too slow, I will run out of time, but it's in the plan. I will shift up 2 gears or so to the end. I'll finish in time. Okay, just to have these 3 points again that I will discuss. So let's look at the NNLO calculation. 2 to 2, for example, Muller. You see in gray, this is the leading order calculation. Very easy. 2 to 2 matrix element, you calculate it, integrate over the phase space, you're done. Next to leading order, you calculate the virtual corrections and the real corrections. They are divergent. You integrate over the phase space. They are divergent, is regularized with dimensional regularization. You put them together and you get the next to leading order cross section. Next to leading order, you calculate the 2 matrix elements. You calculate the 1 loop matrix element with 1 additional radiation. And yes, you calculate the 3-level matrix element with 2 additional photons radiated. You integrate all of this over phase space. It is divergent. You combine it in a particular way, and namely this, what I call this FKS method, to cancel the singularities in a fully differential way. And again, here, see, for example, this one here. I've drawn a nice diagram, only vertex correction, but of course there are all of them. And here, for example, you have pentagon diagrams. You have a box as well with additional photons. So you have 1 loop pentagon diagrams that you have to calculate. And you could say, oh, this is very difficult. But when you go to one of these QCD LHC people in one lovely morning and you say, ooh, I have to calculate 1 loop pentagon with full masses, then they will say, okay, and what do you do in the afternoon? Okay. And why wouldn't we use these techniques? And we will use them. Okay. It's actually a little bit more complicated than that. In fact, what we're going to use for all these things is a code called open loops. And if you ever have seen a chainsaw, open loop is a chainsaw. It just does this. You give it the momentum, and it spits you back the matrix elements at 1 loop. But we will see there is a slight numerical problem with it because of the fermion masses. And we have to correct for this. And this is what I call nexus of stabilization. And the other problem we have is there's a problem 2 that has to do with diagrams like this. They are generally not known for massive particles. And so we have to do something about this, okay? And this is what's called, how we deal with this is what's called massification. And this is in fact where we do make an approximation, even though I made this very bold claim at the beginning. In fact, there we have to make an approximation, but I'll explain this. So those are the 3 points: infrared subtraction, massification, and next to soft stabilization. And let's go to the first one. And this you all know, right? So you have a radiative matrix element. Here it is, a matrix element, an additional photon. And you look at the soft limit of this, you get an Eikonov factor times what we call the reduced matrix element, the one without this photon. And this factor you all know, and those people who do the soft photon approximation actually use this and only this and drop everything here. So that's very well known. But sometimes not appreciated enough is that in QED, this is not only true for the 3-level, it's true to all orders. If this is a 7-loop amplitude with an additional photon here, and you look at the soft limit, you get exactly the same Eikonov factor times the 7-loop amplitude without the photon. In QCD, this is not true at all. You get corrections to this thing here. In QED, you get no corrections. And this is an unbelievable simplification. So we use this. Now, so what we have, we want to integrate. I mean, for this part here, let's say we are here. I'm not dealing with this. I consider this solved. So I'm dealing with this only. So we have to, for example, integrate this. Then we have this radiative amplitude that we have to integrate over the phase space. This is something that's very complicated because you might make really fancy cuts on this thing. It's not a total cross section, right? With angular cuts, energy cuts, whatever. It's complicated and it's divergent. That's not good. And so then what we do, and this is the subtraction method. So we just subtract this bit and add it back. And we add back precisely what we subtract. And so then we have this, oh, I have this one here. So then what we have here, this is still complicated, but it's finite. So I integrate it numerically, Monte Carlo. This one is divergent, but it's easy. So I calculate it analytically, or at least the phase space integration of this additional photon, I do analytically. And I've not made any approximation at all. And then look at this bit, how it looks, right? So you get, so I often use this psi. Psi is the photon energy, just dimensionless, it's scaled with some arbitrary large scale or whatever. And then these integrals, the way they look is d psi psi, this is from the phase space, and 1 over psi squared, and this 1 over psi squared is here. We see this is photon is 1 over, if the energy of the photon goes to 0, this goes like 1 over psi squared. And then you have to integrate this. And every mathematician says that's very unhealthy because you have a 1 over psi singularity. And if you had a photon mass, you would say, I make not nil here, but I make lambda or m gamma or whatever is here. And we say, no, the photon remains massless. It can have energy 0. We use dimensional regularization, and we get this 1 minus epsilon. This is the same epsilon as Fred had. It's the 4 minus d is 4 minus 2 epsilon. And we do this integral. And then you get an integrated Eikenhoff factor with the infrared singularity as a 1 over epsilon pole times this one. That's the divergent but easy bit. And then you have the complicated but finite. And we write this just like this. We do it numerically. We write it typically in terms of these distributions acting on a test function. But that is really just the original matrix element. And then psi goes to 0. Or more precisely, then psi is smaller than a certain parameter. I'll come back to it in a minute. We just subtract it. That means when the things wants to become singular, say, no, I subtract the singularity. And this is in 4 dimensions a finite quantity. I have this psi c here. So we integrate from 0. We would have to integrate to 1 in principle. We could. But on purpose, we say, nah. Let's leave this as a free parameter. As long as I have the same here and here, I still subtract the same thing as I add back. And we leave this as a sanity check, okay? We can use any psi c, but our result has to be independent of that. And I'll come back to this when you see that's a very useful sanity check. So this is what we call the subtraction scheme. So we do not write the one loop correction as a virtual part regulated with a photon mass, plus a soft emission part regulated by a photon mass, plus the resolution parameter, and then might or might not add the hard emission determined by this omega. We do not do this. We write our one loop correction as an n particle part plus an n plus 1 particle part. Both of them, and here they are defined. You see, this is an n particle phase space integration where we have the one loop matrix element that has 1 over epsilon pole, and this thing that we add back, the integrated Eikenhoff, has a 1 over epsilon pole, and they cancel thanks to Bloch-Nortzig. And so we have a finite thing here that we integrate. And this depends on this psi c. And here is the subtractive part that also depends on the psi c, and that better cancels between the two things. And it's for us actually not even easily possible to neglect hard emission from the photons. It would require additional work to sort of take it out here. It's in there from the beginning and will never go away. This is about 30, 40 years old or something like that. It has been used 752,395,000 times for the LHC. Completely standard. Why do I make a song and dance? I go now to NNLO, and there it is. NLO, I have an n particle part, n particle part, an n+1 particle part. And NLO, I have an n particle part, an n+1 particle part, an n+2 particle part. Here I need the 2-loop matrix element. It has a 1/epsilon² singularity. I have the 1-loop matrix element, which has a 1/epsilon singularity, with an additional radiation, which gives me through the integrated cycle another 1/epsilon. I have the 3-level matrix element with 2 emissions that are integrated over the given 1/epsilon². They all cancel, give me something finite. And you see here is an exponential. This is the Jenny-Frauchi-Sura exponential that develops. This is sort of what you use when you use exponentiation. And then we have these other 2 parts again, which are subtracted and are finite. Everything can be integrated in 4 dimensions with any cuts as long as they are inference safe. And now let's look at this psi-c dependence. Now I said this better cancels, and here is an example. This is a plot. This is especially for Ron. So far he had to suffer through so many equations. I thought it's time for a plot, and here it is. So it's I take this example, muon electron scattering. Point like muon. Why don't you think of it as electron proton scattering with point like proton? And we look at what we call the mixed corrections. And mixed for us is TPE. But T now stands for 2 and also for 3, because we are next to leading order. So this contains all the 2-fold and 3-fold exchanges for a point-like proton. Here you just see the NNLO coefficient, only the NNLO coefficient. And here you see this psi cut, this arbitrary parameter. Here is 1, the maximal value, and it goes down to 10 to the -3. And up here you see 3 curves, an orange, red, and green one. And the orange one is the n particle part, depends on psi cut. You have in green the n+1 particle part, depends on psi cut. And then you have the n+2 particle part, depends on psi cut. Now this is the moment of truth. You add them together, cross your fingers, and you get the blue line, okay? And if you now tune in on the blue line, you should see a blue shade here with a bit of luck. So that's just the difference between 1 of the full one minus the averaged one. And you see for all psi cuts, it's perfectly consistent. So it's psi cut independent. That's a bit of a cheat. Whenever you do this the first time, it's never psi cut independent. It's like for the experiment, it's like the alignment of your detector, right? The detector is never aligned from the beginning. You have, then you say, oh, something went wrong. Oh, here's a numerical problem here. Oh, there's a screw here, whatever. And then you do until it looks like that. And then you show the plot, okay? But then you're confident. We got it right. We got it right, okay? So, and that's how we do this. And now you could say, well, okay, why stop there? If you wanted to go to n³ LO, the subtraction would just go on. You will get 1 term more, and you can go to 7 loops. And from a mathematical point of view, if you knew all the matrix element, that would work to all orders. And you could just do it, plug it in, evaluate it, and you're done. From a practical point of view, this is of course wishful thinking. No, I mean, in practice, you have several problems, and so far we had the point 1, that was the nice bit. Now I come to the not so nice bits. That's 2 and 3. This is the additional everyday problems, the alignment problems that we have when we want to do these calculations. Good. So go to point. Okay, just to sort of do this thing again, right? So this is now, for example, for Möller scattering, where we have done all of this at next to leading order. So what you see here is the amplitude, and here on the other side, the complex conjugate of the amplitude. So this is a picture of the amplitude square. You have photonic and fermionic corrections. Let's focus on the photonic ones just for fun. Then here you have the double real radiation square. Here you have the real virtual corrections. Here is a pentagon diagram among many others with one additional emission and multiplied by the 3-level real one. And here you have 2-loop integrals times the bond, and you have to put all of these things together. As I said, for open loops, for example, for these at one loop, at one loop here, we use open loops, and it just gives us the numbers. But we have some numerical issues here, which I'll describe in point 3. It is to do when we go into a corner of phase space where this emission is first of all collinear, and on top of that even soft. Then we have something to sort out, and that we do with next to soft stabilization. But I think Fred, you have a question.
In the Møller scattering, you also have photonic. What did you look on?
Pure intermediate photonic part.
Was electron positron going into?
Møller is electron.
Sorry, I'm from Baba.
But you can actually cross it to Baba, but yeah.
Sorry.
Okay, so that was this point 3 I will come back to, and then the point 2 is the next one. If you look at this, so I said, right, you just need the matrix element with massive electrons at 2 loops. They are not known. They are just, we can go to our QCD friends and please, but we don't have it. And how do we deal with this? We need masses. So and how we deal with this is what we say massification, and this is what I'll describe next. And just to give you an overview of what is known and what is not known with respect to 2-loop integrals. If you look at something like this, where you have a 1-to-2 process with massive electrons, at next to leading order, the full mass dependence is known. Okay, and it's known for quite a while actually. I mean, that is relevant for one photon exchange in the proton case. No, that's exactly this. That's known. Now, if you have the same topology but 2 different masses, so that would be related to muon decay into electron and neutrinos. You see, you just add 1 mass here. It's 2 different masses, and it is 14 years more difficult. Okay. They are known now, but not so long, right? And you get more complicated functions. I'm sure you all remember Johannes Blümlein's talk. He had these funny H's and things floating about, harmonic polylogs and whatever. Here they are, right? And they are more generalized ones of those. And you have, this is just functions that pop up in the expression. When you go to 2-to-2, you have a massive line and a massless line. So we are approaching Baba. So you have 1 mass and the other one is massless. The integrals are known just about very recently. This calculation is done in the context of muon. If you now want to have both of those massive, not all integrals are known. Some planar ones are known. And you might think, okay, give them another year or 2 and we will be there. And I doubt it, because you see from here to here, you get an entirely new class of functions, so-called elliptic integrals. It's really not a little bit more difficult. It's a completely new class of problem. And you never know, but you shouldn't expect that this is soon available. I'd be happy to be pleasantly surprised, but you shouldn't take this as a working hypothesis. And just a quick note to this function. I will rush over this. Right, so you all know logs and dilogs, you love them. And if you have just 1 scale in your loop integral set, then this is pretty much anything you can get. It's all functions of 1 scale. If you have masses and more scales, you like A1 to AN and Z, then you get sort of generalized, not just polylogs, but multiple polylogs. And they have, mathematicians love those, right? And then you can play with those. What's for us important, if someone gives you a matrix element with hundreds of these beasts in there, you have to evaluate those numerically. And you better do it fast because it's a Monte Carlo. You have to do it again, and again, and again, and again, okay? And so what we've done is we have this function called handy G that we have developed on purpose to evaluate these beasts fast and reliable. But this is just a little thing. So do not expect to have the full massive two-loop amplitude ready anytime soon. If we have it, wonderful, thank you. If not, we have to help ourselves somehow. And this is this massification bit where we, with a sigh of anger, do make an approximation. Okay. And this approximation is based on something you have actually seen more than once already in this workshop. Again, maybe if you remember Blumlein's talk, he had something similar. He had a massless hard scattering, and then something he called radiator that added the mass effect to this. And really, so the basic idea is that the amplitude with a mass. So let's talk about muon electron scattering again. So this is the muon line. The mass is completely taken into account. This is the electron line. And I know it only for massless electrons. And this is what I mean by A0. The little m is the electron mass. I set it to 0. So this is known. But we would like to have this one. And so we can, with sketch of collinear effective theory as a conceptual tool and the methods of region, which is a way that tells you how you expand integrals in small quantities, and m is considered to be small. You can find the structure of this amplitude as this massless one times so-called set functions that convert the collinear singularities of a massless electron into masses. There's also a soft part, but in QED this contains only fermion loops, which we calculate separately anyway. And the nice thing is these sets here, they are universal. Once you have them for one process, you have them for all processes. And what this gives us is really gives us the massive amplitude up to terms that are polynomial suppressed with n square over q square. And yesterday in the talk of Igor, you've seen he had this as well, right? He had the massive one loop and he dropped these terms. And as long as n, think of this as the electron mass, and this is the muon mass or the center of mass energy, something like that. So this is small, okay? If it's not small, we're stuffed, okay? But if it is small, we can use this one here. And it's actually numerically a very good approximation. And I convince you of that even more, because what we do here, and that's plot number 2, we look at the muon decay that we can calculate exactly with the whole electron mass effects, because the integrals are known, to its massified version. Here is the positron energy spectrum of the muon decay from 50 MeV down to 0. And here you see only the two-loop coefficient, right? 311 and one loop, we do with the full mass dependence anyway. This is just the two-loop coefficient. You're supposed to see 3 curves here. You see the green curve, which is the logarithmic approximation. You have it just there to guide the eye. And then you see 2 more curves, but you don't. Okay, there is actually an orange curve and a blue curve here. The orange curve is the massified result, and the blue curve is the full result. Okay, not so bad, no. And you can now look at here the mistake that we have made. Here is a 10 to the 5. So the mistake we made is 1, 2, here 1/2 times 10 to the -5. Okay, so the mistake is actually not larger than the alpha cubed correction that we have anyway. Okay? And parametrically the mistake is alpha over pi square, n e square over mu square. This is the n square over q square, potentially times a logarithm. So it's an approximation, but it's a very good one for small fermion masses. And that brings me to the third point. And this is this, yes.
Do I understand correctly that massificators include all logarithms of Lepton mass, and there are no more logarithms of Lepton mass there?
In principle, there are also logarithms in
soft.
this part here. But if you focus on the photonic corrections for the moment, the answer is yes. And indeed, when you do a structure function approach or a fragmentation function approach, it's exactly this thing here that you then could, in some sense, with RGEs, get an electron parton distribution function or an electron fragmentation function. It's all only to do with collinear emission along this leg. And that's why you see it's process independent, a collinear emission, not the soft one.
Yes, thanks. And the other point, quick clarification question, there is also terminology called collinear functions. How is related to this terminology?
It's very closely related to this function. I mean, it's typically in QCD where they have collinear functions in this, but it's sometimes they call it the check function or the collinear function. It's all very closely related to this.
Yeah, I mean, the point that they have to have then the same logarithmic structure, and I understand.
Yes, so then I mean,
probably not finite pieces.
So what all of they do is they take this 1/epsilon collinear singularities from the massless electron and convert it to logs of m. Important thing is we also include the constant terms, okay? But we do not resum those. It is fixed order, right? It's not like a PDF where you then actually resum the things through the RGE. Here, it's just really a fixed order term by term. It's up to order of alpha squared in our case.
Okay, so it contains some fixed number of real photons. Do I understand?
If you want.
Okay.
I mean, if you want. I mean,
fixed number of real photons
and two collinear emissions.
Not real, only virtual. Only virtual. Okay.
It's like in the PDFs, the Altrelli Parisi, right? It's really
yes, but this is matrix element level. So this is not real. There's no real version. It's just a trick to calculate the two matrix element, and you can sort of relate these Z things to something in SCED, the collinear functions in SCED, by essentially renormalizing them. These things are divergent, and collinear functions in SCED aren't. But this is because how we do it. Okay.
So this is where we want to go now. So this is this, actually, just to remind you where we actually are, we are now at this part here. We go back to this one. As I said, in principle, it's trivial. Use open loops to get the matrix element, do the phase space integration, and you're done. And now I tell you, it's not quite as trivial as we might have hoped. And this is the following here. Let's look at this plot here. So what we here have is psi that gives you the energy of the emitted photon. Again, remember, it's a scaleless parameter that specifies the energy of the emitted photon. Here psi is large, here psi is small, 10 to the minus 7, 1. Okay. And what you see here is the difference between the calculation, the exact calculation, and various approximations. Now, I should say we have done this, as I said before, for a particularly evil point, namely when this photon is not only soft, but also collinear to one of the external legs. So we really go into the full phase space, into a region where it really hurts, where everything that could go wrong goes wrong. Okay. And now let's look at the open loop result, and this is the blue line here. Okay. And here you see the difference with respect to the exact matrix element. By the way, the exact matrix element is a mathematical calculation where we can use 200 digits if you fancy it. So all the cancellations go away. We can use it. Whatever.
There's no approximation, right? Like
approximation is that we use double precision in the other two lines that you have. Like you said earlier, there's the exact and the various approximations. The approximation is double precision and quad precision.
Let me explain the plot. Okay. So we have an exact result, which is the Mathematica. Exact means 50 digits, if you want. And here you have the energy getting smaller and smaller. And this is the open loops, the standard open loops result. And you see here the difference to the exact one is 10 to the minus 9. So it's very good. And you make now the energy smaller and smaller, and then it starts to go bonkers. At some point, it's 10 to the minus 3, and here it's a random deviation 10% off. It's just not stable anymore, open loops. Now, in defense of open loops, we could use quad precision. That's the red line. And then it's always good to 8 digits. This is 10 to the minus 8, 10 to the minus 9. So we could just use quad precision, which is a private feature we have, but it takes time. It takes time. Okay. Now what you see here is the soft limit discussed as before. If the photon is not soft, it's a very bad approximation. You make the photon softer and softer and softer. It gets better and better and better. But now if you're here, you don't quite know what to do, okay? Open loops isn't quite good enough, and the soft approximation isn't quite good enough. And so what we now do is we help it.
Sorry. Video turned itself off.
They don't see my pretty face. What a shame.
Let's just see what you're pointing.
Okay. So how do we solve the problem? Well, we do what we do best. We steal, okay? And we go back to a theorem that is only about 70 years old or so. It's called the LDK theorem, low order Crow theorem, where you actually can improve on the soft limit. So the one that we all use is the one that goes like 1 over E gamma squared when E gamma goes to nil. And then you can improve this to and include the 1 over E gamma terms, not only 1 over E gamma squared, but 1 over E gamma. And this also has a universal structure. It has a differential operator. This is just a factor. This is a differential operator. It's not so surprising. You do, naively speaking, something like a Taylor expansion. So we have a differential operator. And that was known a long time ago. Now we want to do this at one loop. I said this here does not get corrections at one loop, and not at two loop, and not at three loop. But this one actually does. And we have evaluated those. It has to do with soft contributions, but soft in the sense of method of regions. And we can calculate those and get a universal structure of those. And with those, we go now back to the plot that we had before. And now I cannot advance my slide.
You might want to click on it. Jan had a question in the chat.
Okay.
I don't know if you want to address that now.
It's fine.
Or, Jan, do you want to just ask your question?
Yeah, I mean, instead of going full to quad precision, have you tried Kahan summation in your histogramming?
So you have tried what?
Kahan summation. Where you
I
have
don't know what Kahan summation is.
So that's a way to make numerical sums more stable. You have essentially two doubles, and you do some tricks. So it's numerically less expensive than quad precision, but might be like a step in between where you get some of the precision back.
Okay, so I have to give more justice to open loops. When I say just double precision, that's not true. In fact, that's really just what is the standard default mode by open loops. And they're very sophisticated. They do double precision and have internal checks. And whenever their internal checks fail, they go and do quad precision calculations. So it's much more fancy than just double precision. And this open loops is a tool that has been developed again over 10 years by 10 people. And the reason why this problem shows up is because when they developed it for QCD and did not have small fermion masses in mind. And I don't feel in a position to go and tweak a little bit what they have done over the 10 years. So,
sure. It's likely that they do something similar then.
I guess so. I mean, it is indeed much more clever than what I just said. Double precision. Okay. They will kill me if is this recorded? Oh dear me. Okay. So, okay. So now let's go back to, and this is the same plot that you have seen before, but there's now one line more, the green one, which is the next to soft. And you see before we went here and didn't really know what to do here. This is a deviation of 10 to the minus 2, 10 to the minus 3. And now if you use the green curve, we can say, ah, when the photon gets too soft a bit, then we use the next to soft approximation. This is 10 to the minus 5. And I have to stress again, this is just in a small corner of phase space. We get the matrix element always better than the 10 to the minus 5 or something like that. And again, if you now, well, ooh, they're fishy, what are they doing? So now it still doesn't work. Let me try again. Okay. Let's look again at the mixed corrections. Mu electron, mixed correction, just the real virtual part. That depends on Xi cut, right? We choose a particular Xi cut. We do muon inspired cuts, whatever, it doesn't matter. And what you see here is two curves. Two curves again, have you good eyes? Yeah. So this is, the blue one is the standard open loops with next to soft stabilization. And the orange one is open loops quad precision. And here you see the difference. Here it goes through 0, so mathematical difference is infinity. But if you look at here, and this is again just the two-loop coefficient, the difference is tiny. It's tiny. And if you want to have numbers here, you have the integrated results next to soft versus open loop quad precision, and you see it's not an approximation because within the numerical error of the Monte Carlo, the two agree. And what's then the difference? The difference is 70 days for the orange curve or 4 days for the blue curve. Okay, it's the same statistics used for both of them. Now, if I have the choice between these two, well, if it's holiday, I take this one, but if it's runtime, I take this one. Okay. And it's sort of nice, it's a field theory solution to it. It's a numerical problem, and we have a field theory solution to it. So I'm quite happy about this. And I show this only because of the picture. I want to show you the picture and alert you that there are additional problems, sort of. I haven't told you about how we calculate the vacuum polarization contribution, because we have again just stolen what people have done before and do it again, right? There's many people have wrote that. We actually do it fully massive, okay? And we also take the hadronic part here into account. Okay? I know Hubert has done work on this, and many people have done work on that. We have not invented anything new for this one. We have so-called collinear pseudo singularities. I told you before. In some corners of phase space, we have these large logarithms, numerically delicate. So what we do is we partition the phase space. But in each partitioning, we have at most one collinear region. And then we make a tuned phase space routine. What it means concretely, we say one of the Vegas variables, the integration model, corresponds exactly to the angle. And then this adaptive Monte Carlo is very well capable because there's only one delicate point, it goes there and does this integration numerically smooth. This is a few more, right? Whenever somebody says, now everything is sorted, you know it's not really true. You think it, then you start the code and then things go wrong. And that brings me to my final slide. I mean, LHC, right? Every second talk is about NNLO, and we can also do that in QED. We can also just use their results, adapt it a little bit. So we can do NNLO QED calculations, but you need chainsaws for it, really, okay? Or diggers or whatever, heavy equipment, but you can just take it. So let's take it. That's what we've done. Future steps. As I said, we have for lepton proton, we have, we have point like, we have TPE for a point like proton, but nothing beyond. And clearly, this is something that we want to add and improve upon. Okay? As I said, we were thinking about N-cube-LO for gamma LL. This would also be one photon exchange for lepton proton, but really, if you think, are they crazy? Do we need that in the case of muone? We want to go to 10 ppm. So NNLO is not quite enough. We have to do more. Okay. I told you about the Parton shower, all these things here. Polarized leptons, not yet. They are about to get in the Parton. And again, once more, I want to point this latest thing here. We have this. I know many of you want this. And if you push us hard enough, who knows, you might even get it. Okay. At the moment, it's not there. That's me done.